Okay, so let's try to solve this question together. So this is the stop and think 5.1, and in this case they gave us a pedigree, and they tell us the following information: that there is a woman. Yeah, so here it will be this one because it's a woman, and they give us even the indication. So this 1 and 1, that is heterozygous. Okay, this is an important information, and it's a heterozygous for a what? For an X-linked hemophilia. Uh, hemophilia A, which result from inadequate levels of blood clotting factor 7. Okay, that is an interesting information. We don't need to here. It's not important the which factor it is, that which type of hemophilia. The important information so far is that we know that there is a female that is heterozygous, and this is the hemophilia. This disease is X-linked. Now let's go to the next part. The next part says the normal level of factor 8 plasma, and here this is another part that is important, is that the normal is 120 nanomolar, but they could be other levels, that it could be 60 nanomolar, sorry, and it will be also considered normal. Yeah, so this is a, so let's put into here, this is considered still normal, although there is a low level of the plasma. Okay, so and here we have the two questions: which females in the pedigree are likely to be heterozygous for the mutation? How you can tell that? And finally, what is the difference between homozygous and heterozygous females? So in the following slides, we're going to try to answer these questions. So now let's go and see the pedigree. Okay, so there are so many things that you can get from this pedigree. So you can say that this is a male, this is a male, and this is a male, because they are all squares. And if you see, the levels of the plasma are different. In particular, 7 is very different from everybody. So this one is the one that will have an abnormal. You can also say that, okay, this one is a female, and actually all of these ones will be females. All of these ones will be females. Okay, and if you see, there is a lot of variation also in the females. Okay, so that is an important information that you can see. And now let's go and start looking for the genotypes. Yeah, and with the genotypes, there is something important that they already gave you. You know that this is a heterozygous, so that it has the disease, and you can start making connection with the plasma. So they told you, this can be 120, and when you have 120 will be normal, yeah. But if you see, this one is not 120, this one will be 7.6. So this one, as is heterozygous, it would be from this group, yeah, from this one, that is the second one. Yeah, the female will be in the one that are considered normal, not because they don't have one faulty gene, but because they don't have so low expression that they still have some of the enzyme, some of the factor 8. So let's go and continue seeing the purple one, the ones that are normal, the one with the higher nanomolar. So we have definitely one that is 1.29, you have 4, and we have also 5. But now let's see the ones that are from the other group. Yeah, the ones that are from 60 to 120, that are the ones that are considered normal. Yeah, although they have a lower expression. And if you see, 2 and 3 are from that group, 6 is from this group, and definitely 7 will not be from those two groups. Yeah, this is much lower. So this will be the one that is lower than 60 nanomolar, so it will be an abnormal level. And remember that this is a male, so this here they give us very interesting information that the lowest that we have there is the one that is a male that only have one X chromosome. Okay, so let's try to start now making a connection between the phenotypes and the genotypes. So the levels of the nanomolars and the potential genotype. So, and as we know that they should be X and Y and or X and X, so it makes life much easier. So for example, in number 2, number 2, it will be very easy. X and number 2 will be X and Y, so it has only one chromosome, and they didn't talk that this chromosome is affected, and if it was affected, this number should be very, very low because it only have one X chromosome. So it's not exactly the highest, it's not in this group, maybe because it only have one X chromosome, or because it's in the threshold, but these ones, it can be considered in this one, in the ones that are completely normal. However, the blue ones could be ones that it maybe is more likely that they can be in this second group. And finally, this one, let's put it in. This one, it could be a male that only have the faulty X chromosome that have the disease. Okay, so here we fuse the information from the genotype and the phenotypes. Okay, and it helps us to start establishing some likely connections. Okay, so to answer these questions, here we will say that the females who are likely to be heterozygous for the mutation, as we said before, it will be 1 from the generation 1, put it in red, from the generation 1, the first one, from the generation 2, number 2, from the generation 3, from the generation 2, number 3, and also from the generation 2, number 6. Why? Because they are in the second group, between 60 and 120 nanomolar. Okay, and the reason for the difference between homozygous and heterozygous in females is because there is something called X inactive principle. Okay, and you have heard a lot about that, and Jamie talked a lot about that in his presentation. So you can give a look to Jamie presentation, or you can go to my video lecture to talk about this. Right now, I just want to remind you, okay, so we were able to answer the first part of the question. We were able to find the reason why, that it was the X inactivation principle, that the one that get inactive can be or one that are the normal, or one that it could be the one that they are sick, so that can make a difference. And in that way we can answer this question. If you have any doubt, just let me know.